I want to talk about correlation coefficient. How many people have ever heard of correlation coefficient? All right, so did you have it in prob and stats?
Psychology.
Psychology? So the social science. Excellent. I really think that physics ought to be taught first, and then chemistry, and then biology. And the reason is that when you are dealing with physics, there's really only a few laws that govern how the universe works. In chemistry, it's a bit more fuzzy. Well, let me back up a second. When you roll a marble down a ramp, and you've got a stopwatch, and you time it, you pretty much know how far that marble is going to go down the ramp in a certain amount of time. There is a right answer for most things, for most Newtonian physics. When you get into chemistry, and you guys have just come from there, or maybe you're taking it at the same time, when you start looking at chemical reactions, you know that there are limited reactants, and that maybe the chemicals you're not using are not perfect. You're going to have some leftover product. Everything's not going to go to a complete reaction. So, you should get so many grams or moles or whatever products of a chemical reaction, but you might not. But in general, that's, it's a little bit fuzzier. When you're dealing with life, life is complicated. People are unique. Personalities are different. And so when you're in the social sciences, your right answer comes from a result of statistics, right? So you have to have a lot of data in order to prove your point, because you can say, well, this person, may act this way on this day or not on this way, or this person doesn't have that kind of reaction to this drug. So when they do medical trials, they have to have a lot of people involved in the trial in order to support their claim that this drug is actually going to help people and not hurt people. Right? So in what you've done for me so far, you haven't taken anywhere near this amount of data. But what I've shown up here is a scattering of data. And these, mind you, this is working for linear relationships. Linear meaning a line. If you could draw a line through this data, a line of best fit, then you could model this data with a linear model, with a y is equal to mx plus b kind of an equation. The data doesn't always fall on the line, right? That's why we have to have a line of best fit. The data is a scatter of data. The correlation coefficient is a measure of how well the data fits on the line, right? But just like you have positive and negative slope for the relationship between just like you have positive and negative slope for the equation of a line, you have positive and negative correlation. Now, just by the way the correlation is computed, correlation coefficient is a number between -1 and +1. 1 being very high correlation, perfect, exact. There's no deviation. Every single point falls exactly on the line. 0 meaning absolutely no correlation. There's no rhyme or reason that one responds one way, that one variable responds to the other variable in a predictable way. Remember, when we're graphing, we've got independent variable, dependent variable. Independent variable, dependent variable. What does somebody say? Dry mix, right? Independent variable, dependent variable. So the dependent variable, the value of it is going to depend on whatever the independent variable was. So when you have a line of best fit through your data that's in a positive direction, the relationship between those variables is when one increases, the other increases. And you can see that in the graph. In a negative slope, when the independent variable increases, the dependent variable responds in the opposite way and decreases. Now, if you look at this data, you can't say one way or another whether there is a positive correlation or a negative correlation, right? So when you're thinking about whether correlation coefficient is positive or negative, just think about whether the slope of the line of best fit is positive or negative, and then you'll know. Now then, so positive, negative, no correlation. Between if this is positive correlation, so it's either not correlated or it's positive correlated, this is definitely more organized than that. So this must have some value, but everything is not perfectly on a line. It must have some value between 0 and 1. And everything's not following on a line right here, but it's certainly more organized than that. So the correlation coefficient's got to be between 0 and -1. So we're just going to qualitatively guess what the correlation coefficient is for these. I don't know. Somebody can see. Mr. Gibbs, what would you guess the correlation coefficient would be for this? It's not 1 because it's not perfect. Everything doesn't fall on a line. It's positive, so guess a number between 0 and 1. Just on a scale of 0 to 1, how well does all this data fit on a line? 0.55. Okay, dandy. That's a dandy number, right? Okay. I have no idea what it is. I mean, we're just talking. Now, Logan. Okay. On a scale, there's an outlier. On a scale of 0 to 1, how well correlated is this data? 0.9. Okay, good. Good. All right, so already you guys can qualitatively look at data and tell me about the correlation. And that's really all the correlation coefficient is doing for you. The correlation coefficient comes from a linear regression analysis. And in your calculator, you will see a function called linreg. In your calculator, you go into stat mode, you go into edit, and then you're presented with a table, and you enter your XY data, and then you press stat again, and then you go to function or calculate, maybe calculate it is, and then you scroll down and you find the function that you want to use. Linreg is one of those functions. The linear regression analysis does a least squares fit of the data. All right, this is not math class, and I'm not going to go into the details of this, and this is something you certainly do not want to calculate manually. This is why we have computers do this. What the computer does in order to do a least squares optimization of the data is it draws a line. It takes a hypothetical line, line of best fit. It takes a line of fit. Maybe it's not the best at this point. It's going to figure out what is the line of best fit. You can do this. The human brain is awesome at being able to draw a line through the data. And if you have a clear ruler and you can make sure that you have as many dots above the line as you do below the line, you are going to come out with a pretty good line of best fit. But analytically, someone's going to question, whether your ability to do that or not. So it's best to leave that to a calculator. And here's how the calculator does it. It draws a line segment from the data point to an arbitrary line going through the data. Okay? Every data point has a little line segment associated with it. Okay? And then what the computer does is it adds up all these little line segments. Computer can do this really, really fast. It throw an arbitrary line up there, draw another line perpendicular to it that goes to the data point and adds up all these little line segments. Then it draws another line. Maybe I should do another color. Wow, that was a pretty good line of best fit to start with. Maybe it'd go like here. Then it draws another line, and then it draws another set of points. It draws another set of line segments from those data points to the arbitrary line. And then it compares the two. Was the length of the line segments for the previous line longer than the length of the line segments for this line? It goes for the shorter addition of line segments. Probably could have said that better. It's trying to figure out, it's trying to draw a line that comes as close as possible to as many data points as possible. Does that make sense? That's what you're doing visually. The computer does it by drawing little line segments and adding them up and comparing them to various lines that go through the data. All right, that's what a least squares fit of the data is. The result on your calculator, it gives you the equation of this line. I think if you're using a TI-84, it doesn't use M, it uses A. It tells you what A is. It tells you what B is. It tells you some other stuff, but what we're interested in is R and R squared. This is the correlation coefficient. Correlation coefficient is R, and R squared is R squared. R squared just makes sure that you always have a positive number to deal with. So if you have data that is has a negative slope to it, a line of best fit that has a negative slope, then you're going to get a negative R, but if you square that, you're going to get a positive number. So what we are actually going to be looking at is the R squared value, so we don't have to worry about whether it's positive or negative. We're just trying to find out how well the data fits to the line. Okay? We're going to be working with our calculators, and we're going to make sure that we know how to do this. Some of you will say, hey, I don't get R in your TI-84 when I do exactly what you told me to do. You have to go to a setting and turn it on so that it tells you R. So don't worry, you don't have a cheap calculator if it's not telling you R. You just need to enable that function. What's the point? I started out this lesson by going through a very arduous process of showing you that a 0% error is not really a 0% error because your measurements were really sloppier than that. In the one student's case, your 0% error was actually a 3% error, which is not bad experimentally. I expect you to be able to get 5 or less. You get more than 5, you got some explaining to do. Maybe it's 10. We'll decide depending on the experiment. But that was an arduous process. And heretofore, if you're in middle school, you say, hey, I got a 0 experimental error. The teacher said, oh, that's very nice, and patted you on the head and said that's a good student. But now we're going to look a little bit deeper and say, really, did you just get lucky? Because understand this. Here's what I mean when I say getting lucky. You could go into the lab and you could get wild data. You could draw a line of best fit, and all the scatter of data averages to be perfect. That's what I mean by you get lucky. Another person, so this is you got lucky. All right. This line being the theoretical value. On average, you got the same answer. This is the theoretical value. Another person goes into the lab, has very good experimental technique, this person nailed it. You nailed it. Not only did you match the theoretical value, but your correlation coefficient is really, really low, and it's tight. There are 2 more examples of what can happen. What if you got tight correlation in a pattern like this, but your theoretical value is down here? Mr. A, I've got really good experimental technique. I've got some experimental error here, but obviously there's some sort of bias. There's a systematic error going on. This is systematic error. And I'll ask you, how did you read the graduated cylinder? Well, I just held it right here and I looked at it. Parallax error, right? Wouldn't that be a systematic error if you always read your instrument not straight and level, but maybe if it was a triple beam balance, maybe you read it from the side, or maybe that's a systematic error. Or you could do the experiment. There's some theoretical value. There's just no correlation at all. Okay. So those are the 4 cases. When you look at your data, you're going to be able, by using the correlation coefficient and your experimental error, you're going to be able to definitively say whether you nailed it, whether you got lucky, whether there was some systematic error. This can also happen if you invert your axes, and or whether there's no correlation at all. And tomorrow we're going to look at your data, and you'll be able to determine it. So what I'm trying to eliminate is kids saying, well, I got a 0% error, but they have sloppy technique. Or a lot of students, when I ask them if they get some sort of an error, and I say, well, what do you think went wrong? And they say, oh, human error. And that's not an acceptable explanation of why you didn't nail it, right? You've got to tell me whether it's a systematic error or whether it was a random error. Right. Okay. That's where we're headed with this.